So good morning, let us start our lecture today. So today we're going to continue our practice exam, practice final. Alright, so in the previous class we were trying to solve for ut is uxx with x being on 0 to 2, t is greater than 0. You have an initial condition ut0 is u2 0 and this is 0. Ux0 is 2 sinus of pi x over 2 minus sinus of n of pi x plus 4 sinus of 2 pi x. Alright? So this is the problem that we were trying to solve. You have a heat equation. You have a first derivative in t is equal to the second derivative in x. X is considered to be on this interval. T is greater than 0. The boundary condition is 0 and 2, but they are both 0. The initial condition is this function. Alright? Now you have to solve it. So the method will be the following. Step number 1. The method is to use the so-called separable method, in which you suppose that tx is equal to tt times vx. Alright? You substitute this and that into the equation, you're going to have two equations, right? So we change the PDs into two ODEs. Alright? So the idea of separable is to separate the variables t and x so that you have two ODEs instead of one PDs. Alright? So when you substitute this and that back into the equation, you're going to get the following. You're going to get v second of x plus lambda vx is 0. V of 0 is v of 2 is 0. This is one equation, right? It's the first one. The second equation is the equation on t. So you have 4t prime of t plus lambda t. T is 0. Alright? This is the way that you split the variables in a partial differential equation. So when you split the variables, you're going to have several separate equations on each variable, and then they become ODEs. So step number 2, you solve the first equation. So when you solve the first equation, you obtain the following. So in the previous class, we get, so this is an eigenvalue problem, right? An eigenvalue problem. And you obtain lambda to be n pi over 2 square. And Vn of x will be sinus of n pi x over 2. Alright? Alright? Step number 1, you solve the first equation. When you solve the first equation, you obtain the eigenvalues and the eigenfunction. The eigenvalue will be n pi over 2 square, and the eigenfunctions will be sinus of n pi x over 2. Right? Step number 2, solve the second equation. This is the first order differential equation. And you obtain Tn is exponential of minus lambda n, which is n pi square over 16 t. you solve the second equation, which is a first order differential equation, so solving to this first order differential equation is very standard. The solution will be exponential of minus n pi over 16 squared t. Alright? So then you multiply sinus and exponential of t. Step number, this is step number 3. Step number 4, what you do is, after the first two steps, you have a basis, which is exponential of minus n pi squared over 16t times sinus of n pi x over 2. Alright? So after you do the first 3 steps, you're going to have a basis. So this is a basis on x. And the other one is a basis on x and t, right? So after you solve the first 3 steps, what you have is utx is the sum when n is going from 1 to infinity of cn exponential of minus n pi squared over 16t sinus of n pi x over 2, right? Alright? So, what you do now is to try to find the Cn, alright? So we need to find Cn. So how do you find Cn? You're going to replace 0 here, and you're going to use the initial condition, which is a little bit complicated, right? So we're going to use, we use the initial condition. Right, so you're going to use 2 sinus of n pi x pi over 2 minus sinus of pi x over 2 pi x plus for sinus of n pi x over 2. Alright? So this is going to give you u of 0, x. And when you replace 0 here, you're going to have Cn exponential of minus n pi squared 0 over 16 sinus of n pi x over 2, right? It's good. So because when you replace 0 here, you get 1. Alright? So I explain again. To solve a heat equation, what you do is, so this should be first order in T and second order in X. Why do you need first order in T? Because when you plug this and that into the equation, you're going to have a first order equation for T, right? And this is solved explicitly. So I explain again. To solve a heat equation which has first order in T and second order in X, what you do is you suppose that UTX is the product of T and B, right? You plug this into the equation, you're going to get 2 equations. One is on X and one is on T, right? So the idea is you change the PDEs in which you have T and X into 2 ODEs in which you have either only X or either only T, right? So when you plug this into the equation, you're going to get a second order equation in X and a first order equation in T. For the second order equation in X, this is a classical eigenvalue problem in which you can find the eigenvalue to be this guy and the eigenfunctions to be this guy. So this is gonna be a basis on X space only. So I'm gonna find the T. To solve for the T, alright, so this is a first order differential equation in T. So what you solve is is that the solution of this equation is explicit. So you have exponential minus this guy times t, right? Now you have something on x and something on t. You multiply them and you're going to get a basis on x and t. Right? So the solution will be a linear combination of everything. Now you need to find this coefficient Cn. So how do you solve this coefficient Cn? You're gonna replace 0 here, right? So you're gonna have u0x is this guy, this is 1. So you have Cn sinus of n pi x over 2 is equal to the initial condition, right? Alright, so now let us try to find Cn. So now you have the following. So you have 2 sinus of pi x over 2 minus sinus of pi x plus 4 sinus of n pi x over 2. Alright? And this is gonna give you the sum when n is going from 1 to infinity. Cn sinus of n pi x over 2. Alright? This is what we found. Alright? So how do you find Cn? You don't need to. This you can say explicitly what is the Cn from the formula. You don't need to do anything. This is like the first midterm.
Fourier series?
You don't have to do anything. You can say what is the value for Cn right away. N pi.
Divide by
This is 2. Right? So, how do you find Cn without doing anything? I don't have to do any computation and I can have precisely what are the values of Cn.
Can you divide both sides by sine and cos?
I can tell you that C1 is 2, C2 is minus 1, C3 is 0, C4 is 4.
Is that just a written out Fourier expansion of that?
Sorry?
Isn't that just a written out Fourier expansion of that? Like
It's not a Fourier expansion. This is not a Fourier series.
Not Fourier series, but like, isn't that already expansion of it?
Well, they're orthogonal. Is that what you're saying?
No, you don't need orthogonal.
I don't know what I'm saying.
No orthogonal.
Is it negative n?
So from this series, right, I can tell that C1 is 2, C2 is minus 1, C3 is 0, C4 is 4, C5 is 6, C7, they're all 0. How do you tell that?
It's a negative n over 2.
Can you repeat the terms again?
Sorry?
Can you repeat what you just said, the terms? The values?
C1 is 2, C2 is minus 1, C3 is 0, C4 is 4, the leftover is 0. How do you know that? Right, so I'm going to write down the form of this expansion, right? So what is this expansion? This expansion will be C1 sinus of pi x over 2, right? Plus C2 of sinus of pi x, right? Plus C3 of sinus of 3 pi x over 2, right? Plus C4 of sinus of 2 pi x, right? Plus C5 of sinus of 5 pi x over 2 plus C6 of sinus of 3 pi x and higher term, right? So what do you see? You see that C1 is here, right? C2 is minus 1, right? C3 is 0 because there you don't see C3. This is 0. C4 is 4, and the leftovers, they don't exist, right? So from this expansion,
Is it Taylor series?
sorry?
Is it Taylor series?
It's not Taylor series, it's just identify the coefficient,
Oh.
right? So you just write this series in explicit form. You see that all of the coefficient of this guy is given here already, right? So you just have to identify the coefficient, right? So identify the coefficient. So you have C1 is 2. All right, C2 is minus 1. C3 is 0. C4 is 4. All right. C5, C6, they're all 0. Right? It's clear. Now you're gonna plug it into the solution. So UTX will be C1 exponential n pi over 16 square t sinus of pi x over 2, right? Plus, so C1 is what? C1 is 2, so I have 2 here. C2 is minus 1, so I have minus e to the pi square over 16 2 pi square t sinus of pi x. Alright, C3 is 0, so I don't care. And now I have C4. I have 4 e to power minus 4 pi square over 16 sinus of 2 pi x. Alright? It's good. So now this is giving me 2 e to power minus pi over 16t sinus of n pi x over 2 minus e to the pi square over 4t sinus of pi x. So this is 4, so you have 4 e to power pi square over t sinus of 2 pi x, right? All right. So the key idea here is the following. This is the expansion, right? And this is the function. But the function is given as an expansion already. So what you do is you just write explicitly the form of the expansion and you identify the coefficient, right? So this sum is C1 sinus of pi x over 2 plus C2 of sinus of n pi x plus C3 of sinus of 3 pi x over 2, etc. Now you identify the coefficient, you find that C1 is 2, C2 is minus 1, and C4 is 4, and the other terms are 0. Now you plug it back to the solution, right? You have UTX is Cn, but extra term is this exponential. So I just care about 2, minus 1, and 4. So for the 2, I have e to the power pi square over 16 sinus n pi x over 2. For the second one, I have minus of exponential 2 pi square over 16t sinus pi x. The last one is 4 exponential minus 4 pi square 16t, right? So you simplify and you get the final answer. Yes?
If you did the inner product to find Cn, would you get a function for Cn?
If you do the inner product, you get the same thing.
You would get a function? I don't see how you would get a function for Cn if you did the full integration.
Now, if you do the inner product thing, you're gonna get exactly what I show you. Why? y. So this is, so I want to find C1, right? I want to find C1. So what is C1? C1 is going to be the inner product of that guy, 2 sinus of px over 2 minus sinus of pi x over 2 plus 4 2 pi x over, and then you're gonna inner product with sinus of n pi over 2, right? And then you have sinus of pi x over 2, sinus of pi x over 2, right? So this is how you find C1, for instance.
What did you see in it?
Even Cn, so let me do it for C1, and then you see that this is exactly C2, right? So why is it? Because when you do this in a product, this guy and this guy is orthogonal, right? So how do you do it? You have 2 sinus of, and you took px over 2 sinus of px over 2, right? This is the guy that have 2, and the other guy will be 0. Right? So this is the first guy. The second guy will be this and that. So minus sinus of pi x, right? Sinus of pi x over 2. And then you divide by sinus of pi x over 2, sinus of pi x over 2. And the last term will be 4 sinus of 2 pi x, sinus of pi x over 2 over sinus of pi x over 2, sinus of pi x over 2. Right? This is what you get. This and this, they are orthogonal, so it's 0. This and this is orthogonal, so this is 0. The level of this is this divided by this, but this is 2, right? So if I have sinus of n pi x, everything will be 0 because of orthogonality. Right? You see what I mean? How you obtain C1? You obtain C1 by multiplying the function with sinus of pi x over 2 and dividing by pi x over 2. Right? So the term that matter is this times this. Right? So this is the first term. This is non-zero. The level is this guy with this guy and this guy with this guy. They're all 0. So which means that you don't have anything, right? So now if I replace this by n, this will be orthogonal with this will be orthogonal with this, and this will be orthogonal with this. So everything will be 0, right? So let me explain it clearer. How you compute Cn? So how do you compute? So this is C1, and you see that this is basically give you 2, right? So now, what is Cn? So what is Cn? Well, n is, say, n is greater than 4, right? Cn will be 2 sinus of pi x over 2 minus sinus of pi x minus 4 times sinus of 2 pi x sinus of n pi x over 2. Alright? Divided by sinus of n pi x over 2. Sinus of n pi x over 2. Right? This is Cn. But the value here is 0 because they're all orthogonal. Right? So this can be computed like 2 times sinus of pi x over 2 sinus of n pi x over 2 dividing by sinus of n pi x over 2 sinus of n pi x over 2. This guy is 0 because this is orthogonal with this one. This guy is giving you 0. The second guy is minus, right? So you have minus sinus of pi x sinus of n pi x over 2 dividing by sinus of n pi x over 2 sinus of n pi x over 2. This gives you 0 because of orthogonality, right? So the last term will also be 0. Remember that n is greater than 4. So the last term is minus 4 times sinus of 2 pi x and sinus of n pi x over 2 dividing by sinus of n pi x over 2 sinus of n pi x over 2. And this also gives you 0. Right? Alright? So basically you just have to identify the coefficient in this way. It's clear? Questions? It's fine. Alright, so let us go to the second. Let us go to the second problem. Right, so let us see. The second problem is ut is uxx. 0 is smaller than x, smaller than 2 pi, right? And t is greater than 0. So you have the boundary condition ux at t0 is 0. Ux at 2 pi, t will be 0. Ux at 0 is 0, is x. So basically this is heat equation. So what is different? The difference is the boundary condition, right? So the only difference between all of those exercises is the boundary condition, right? So the boundary condition determines what? So the difference in the boundary condition in x gives you what? Different basis, right? Yes?
Isn't this the homework?
Oh, sorry. Is it the homework? Oh, sorry. So this is alpha squared. X is going from 0 to pi. Ux at pi is 0. Alright? So, and this is 3. Sinus of pi x over 2. Okay. Right, so this is alpha squared. Alpha is any constant. Right? So the only difference is the boundary condition. So the boundary condition will give you a different basis, but it's the same, exactly the same method. All right. All right. So let us try to solve this problem. So the method is again separable, right? So step number 1, you want to try to find the equation for the ODEs that are associated to this equation. So I'm going to suppose that the solution is separable in x and t, right? The solution is the product of tt and vx. So those are two independent functions of x and t. I'm going to plug this back to the equation. So I'm going to do ut. So ut will be t prime in t vx. All right? And what is uxx? Uxx will give you tt times v second of x. All right? So I explain again. So suppose that so the first step is always to try to find questions.
Is that sigma x over 2 or 6x over 2?
This is alpha.
No, sorry, the 3 lines below.
This is 5.
Yeah.
Right? So you suppose that utx is tt times vx, all right? So ut will be t prime vx, and uxx will be tt v second of x, right? So this is the kind of problem you're gonna have to do in the final. So when you do this separable idea, you're gonna plug everything back to the equation, right? So ut is alpha of uxx, which means that t prime of t times vx is alpha squared tt v second of x. All right? So you have what? You have ut is alpha squared uxx. So t prime of t times vx, which is ut, right? And the other guy is alpha squared tt v second of x. Now you do separable. So you have t prime over t is, so here I have alpha squared is v second of x over vx, right? So here I'm gonna divide tx to the left hand side and vx to the right hand side, right? So I'm gonna have t prime over alpha squared t is v second over v. All right. So why do I divide alpha over here? I divide alpha over here because this is first order and it's easier to solve. Right. So this is the function of t, and this is the function of x. Right. So this is a function of t, and this is a function of x, and those functions are equal. Means that they have to be a constant. Right, so I'm gonna put this to be minus lambda. So again, I divide alpha here because it's easier to solve. I want to try to avoid the second order, so I put the alpha to the first order, right? So I'm gonna obtain two equations, right? So I have v prime over v xx is minus lambda. This gives you v second of x plus lambda vx is 0. This is the first equation that you have, right? The second equation is t prime of t over alpha squared tt. This is minus lambda, which means that t prime of t plus lambda t is 0, right? Alpha squared. Right? So I explain again. So the first important step is to split the x and the t variables, right? So I suppose that utx is t times v. So t is a function of t only, and v is a function of x only. So this is an equation of two variables, and I want to obtain two equations of one variable so that it is easier to solve, right? So I have ut is t prime v, and uxx will be t v second, right? So I plug it back to this equation. I have t prime v is equal to alpha squared t v second, because ut is t prime v and uxx is t v second, right? Now I'm gonna divide t to the left hand side and v to the right hand side. I'm gonna get t prime over alpha squared tt v second over v, and this is minus lambda, right? The left hand side is a function of t, and the right hand side is a function of x, so they have to be a constant, right? Because the function of t is equal to a function of x. That means that they both have to be a constant. So now you're gonna take t prime over t v second over v is equal to minus lambda. So I get the first equation for v, right? I take t prime over alpha squared t is minus lambda. So I get the second equation for t. So the first equation is the second order equation in v, and which is an eigenvalue problem, and the second one is first order, right? So now I have to find the boundary conditions. So u0t is 0, which means that v0 tt has to be 0, right? So tt cannot be 0 since otherwise utx will be tt vx, and this is 0, right? So which means that v0 has to be 0. Alright, so now I'm going to try to find the boundary condition, right? So the first boundary condition I have is u0t is 0. I'm going to plug v0tt to be 0, right? So I obtain v0 is 0, otherwise you're going to have tt is 0, which means that you have a 0 solution for this equation, which is not true. So the second boundary condition, so this is boundary condition. Boundary condition for dx. Right? So now I'm gonna have to find the boundary condition at pi. So you have what? You have ux 0t is 0, which means that vx no, it's pi. Pi of tt is 0, which means that vx at pi has to be 0 by the same reason, right? So the second boundary condition is the condition at pi. You have ux pi t is 0, which means that vx pi tt is 0, which means that vx pi has to be 0. It's clear? Questions? So I explain again. Step number 1 is the most important step, in which you try to change the partial differential equation into two differential equations by supposing that u is the product of a function of t only and a function of x only, right? So now if you plug this and that into the equation, you're going to find two equations. The first equation is an equation of v. This is the second order differential equation, and the second equation is the first order differential equation of t, right? So in order to solve the first equation, you need the boundary condition, all right? So what I'm trying to do here is to find the boundary condition for v. You have u0t is 0, which means that v0 times tt is 0. Tt cannot be 0, otherwise the solution is 0, right? Which means that v0 has to be 0. Similarly, I'm going to use, so I'm going to have to plug the two boundary condition of u to find the boundary condition of v, right? So now I'm going to consider the second boundary condition. So the second boundary condition is ux pi t is 0. So this gives you vx pi tt is 0. Tt cannot be 0, again by the same reason up here, otherwise u is 0. So we have vx pi is 0, right? So now, step number 2. Solve the eigenvalue problem. The eigenvalue problem. Alright, so the eigenvalue problem will be v second of x plus lambda vx is 0. X is from 0 to pi. Alright, and v0 is 0, and vx and pi is 0. Right? So the second boundary condition, the first equation is an eigenvalue problem because it is v second plus lambda v is 0, and v at 0, and v at and pi, they're both 0, right? So in order to solve this equation, you use the classical method that we've learned, the method of the characteristic equation, right? So the characteristic equation. So you have x squared plus lambda is 0. Right? So to solve the eigenvalue problem, there's only one method, which is the characteristic equation. So when you solve the characteristic equation, there are three cases. Two of them will not give you any eigenvalues and eigenfunctions. And the other one will give you all of the eigenvalue and eigenfunctions. There are some exceptional in which one of the first two cases give you one eigenvalue and eigenfunction. And normally, though the eigenvalue will be 0 and the eigenfunction will be 1. Alright? So case number 1. Lambda is negative. Alright? So when lambda is negative, you're going to have two solutions, two roots. The first root will be square root of the absolute value of lambda, and the second case will give you minus square root of lambda. Alright? So this is standard, right? So I explain again. The second step will be to solve the eigenvalue problem. This is the eigenvalue problem that we have, and of course you have to have the boundary conditions. The method to solve the eigenvalue problem is standard. You're going to consider the characteristic equation. There are three cases. Two of them will not give you any eigenvalues and eigenfunctions. There will be exceptional in which you have one eigenvalue, which is 0, and one eigenfunction, that is 1. Right? So let us try to solve the trivial cases. So the first case, lambda is negative. When lambda is negative, you're going to have two roots. The square root of the absolute value of lambda, or minus square root of the absolute value of lambda. And so this gives you Vx will be C1 exponential of square root of lambda x plus C2 exponential of minus square root of lambda x. Alright, so this is what we have. I'm going to use the boundary condition, right? The boundary condition. So V0 is 0, meaning that you have 0 is C1 e to square root of lambda times 0 plus C2 exponential of minus square root of lambda times 0. Alright? So you plug in the first boundary condition. So this is C1 exponential of this guy and C2 exponential of this guy. Both are 1, so I have 0 is C1 plus C2. So C2 has to be minus of C1. Alright? Now I plug this C2 back into the form of V. So I'm going to have Vx is C1 e to the square root of lambda x minus C1 e to minus square root of lambda x. Alright? X. Alright? So I explain again. By using the first boundary condition, I'm going to plug 0 into the equation. Right? So by using the first boundary condition, V0 is 0, I'm going to plug 0 here. I have 0 is C1. So here this is square root of lambda times 0. C2, this is square root of lambda times 0. So this guy is 1, and this guy is also 1. So you have 0 is C1 plus C2, which means that C2 is minus C1. Alright? You plug C2 here. You get Vx is C1 exponential of this guy minus C1 exponential of this guy. Right? Now you're going to use the second boundary condition. The second boundary condition is Vx and pi. Right? So Vx will be so you take the derivative of this guy, you get C1 square root of lambda e square root of lambda x, alright, minus C1 square root of lambda e minus square root of lambda x. You take the derivative in x of this guy and you get that 1. So the derivative of this guy will give you square root of lambda exponential, and the second one is this guy. Right? So I'm going to replace pi there. So Vx at pi will be, so this is 0. So this gives you C1 square root of lambda exponential of pi minus square root of lambda c1 e to the power minus square root of lambda pi. Right? So this gives you c1 square root of lambda e to the square root of lambda pi minus e to the power square root of lambda pi. Right? So the second boundary condition will give you 0 is Vx at pi. So you replace Vx at pi, you have c1 square root of lambda, this guy, c1 square root of lambda, this guy. So I put c1 square root of lambda as the common factor. I'm going to have c1, this guy, this minus this. Right? So which means that c1 is also 0. Alright? So which means that Vx is 0. So this is trivial solution. So this case won't give you any eigenvalues and eigenfunctions. So I explain again. Yes?
It doesn't really change it, but should it be plus C1, the second term?
Yes. Thank you. Right. So the first case is standard. Right? So when lambda is negative, you have two roots. They are both real roots. So you have two exponential. So you're going to have C1 first exponential and C2 the second exponential. What you do is you plug the boundary condition into those forms. The first boundary condition is S0. So you plug 0 here, you get C2 is minus C1. You replace C2 here, you get this form of the solution. The second one is Vx at pi. So you compute Vx. You plug pi here and you find C1 is 0, which means that you have a trivial solution. And right, for the second case. It's good? So now let us go to the second problem and the second case. The second case pi is 0. Case number 2, lambda is 0. So when lambda is 0, you have v second of x. This is 0. Alright? When lambda is 0, v second of x will be 0. So v will be ax plus b. Alright? Alright? So the second case is v second is 0. So when v second is 0, you have a linear solution, which is ax plus b. Right? So you're going to use the first boundary condition. You have v of 0 is 0, which means that a times 0 plus b is 0, and this gives you b is 0. Alright? It's good. So the second case is the case when lambda is 0. So when lambda is 0, v second has to be 0. So when v second is 0, v has to be a polynomial of degree 1. Right? So now v0 is 0. So you replace the two boundary conditions. The first one is v0 is 0. So when v0 is 0, a times 0 plus b is 0, which means b is 0. Right? So vx will now be ax only, so because b is 0. Now you're going to consider the second boundary condition. Vx at pi is 0. So which means that a is 0. So Vx will be 0. So this is also a trivial solution. Alright? So the second case, again, the second case is the easiest case because when lambda is 0, you have a linear solution. You plug the two boundary condition and you find 0. Now the last case, right? So the last case is lambda is positive. So when lambda is positive, you have two roots, right? That contain the I. So the first root will be square root of lambda, and the second root will be minus square root of lambda. Alright? That should be the I, because x squared plus lambda is 0, so you should have I here. Right? So then you're going to have Vx will be C1 cosinus of square root of lambda x plus C2 sinus of square root of lambda x. Alright, so this is the general form. So we continue on Friday.